Okay, we're now to the last talk of the workshop by Mariana, and she's going to tell us about Willow.
Thanks, Sanjam, and thanks to all the organizers for inviting me and for having this event here. Since everybody is reminiscing on the last 10 years, Xiao Wang reminded me the other day that he was my intern 10 years ago, which made me a little sad that it's been so long. And now his student is my intern. And also in the interim, I also spent some time in academia as a professor, and one of my former students also happens to be here. So that's kind of the last 10 years for me. Today, I'm going to tell you about this application scenario, which I will call private analytics, and Mantigoni mentioned as federated learning. I'll also tell you why I differentiate a little bit between the two. So what is the application here is we have some server, some company that has many, many users, and they would like to learn information, some analytics about this user population. Now in this world of AI that you try to ship a lot of models on the devices of clients, if you want to claim that you're doing everything on device, where some of these models indeed stay only on device, you might not have any other way to understand, are these efficient? Do they incur errors when the clients use them? So this type of private analytics allow you to get some understanding of what's happening on device and in aggregate about your population. And of course, the goal here is to have a solution that doesn't just bring all the data to the central server, but processes it in some distributed way. And also the goal, ideally, is to use cryptographic techniques. But as I will mention in some of the next slides, this is definitely not the default solution for as people think about it. So I'm saying private analytics, but if you say this to like a machine learning person or anybody else, like they will think much, much more complicated functionality. We will be modest here, and the functionality that we'll think about is that each client will have an input vector, and what we would want the server to learn will be the aggregation of these input vectors that come from the clients. So much more modest goal. So what is the kind of special about this scenario is that you have very limited communication channels. The clients know only about the server. They don't know about each other, so the only way the clients can communicate is to the server. Also, these clients are usually mobile devices that are very weak and very unreliable, which means that you cannot assume they will be kind of responding to multi-round protocols. So, and I will kind of reiterate some of the messaging that has come from previous talks is that like multi-rounds here are really, really kind of disadvantageous for these protocols. So these clients can drop off at any time. In addition to this, the server can control these clients. In fact, the server can pretend to spawn off a lot of clients. So you really cannot distinguish a real client from a client that's just simulated in these systems. So that's kind of the adversarial scenario that we are looking at. What do you want in terms of privacy and correctness? So even though I defined this functionality of we want to obtain the aggregate for the purposes of the server, it's not necessarily obvious that if you want to define this as an MPC system, this is exactly the output you should try to enforce, that you want to enforce an aggregation across all of the clients. Maybe one way you want to say is that maybe you have aggregation over the honest clients. Given this statement that I said that it's hard to distinguish honest from dishonest, and the server might be able to generate n-1 of the clients himself, since oftentimes the servers are the one that choose the cohorts of clients that will participate in a certain round, you want usually to enforce something stronger. You want to add differential privacy to the output of this aggregation. So even if you're in this worst case scenario where the server is simulating all but one of the clients, you're still protecting the privacy of this one client. For the purposes of the usefulness of this output to the server, you do want to guarantee some kind of correctness for the output of the server. And this starts touching to the question, well, what if clients are misbehaving and they're trying to input arbitrary inputs for this aggregation? So one approach to this has been to try to define some validity property for the inputs of the clients. This takes only so much, but that's kind of what we have as technique so far. So we would like to be able to enforce this validity for the client inputs. So now if we're just defining this problem, there have been maybe two classes of solutions for this problem. One of them is what I call single server. So you do assume a single server that is communicating with clients. And then there have been solutions that are in the category 2 plus more servers, in which you assume that apart from this one output receiver, you will have some other helper that you can hire, pay, whatever, that will help you for this computation. And of course, this comes with the crucial requirement for a non-collusion assumption between these two servers. And this makes your life easier in terms of the constructions that you will be using. I just wanted to say that we've deployed solutions in both models. And maybe I'll take a little bit of a tangent from the technical thing to just tell you about these two scenarios in which these two different types of solutions were deployed and used. So the first one, which is the single server, is in the context of this federated analytics and learning that one of the Google groups uses. Basically, there is a cryptographic solution that is one of the options for the backends. This is not meant to be used everywhere. It's an option that different clients can choose to use should they decide this is important for them. So the other solution, which was a two-server solution that we deployed, was in the context of what was called exposure notifications. This was a system that Apple and Google offered during the pandemic that was helping people identify whether they have been exposed to somebody who later tested positive for COVID. So they had this great system that enabled you to find out this information that had very tight privacy guarantees, which basically said that only I can find out whether I was exposed to a person that was infected. And of course, in that setting, there were many health authorities that wanted to know more. They wanted to know how many exposure notifications were sent, in what regions, also tuning the parameters that defined when exposure notification was triggered were a tunable parameter. So in order to understand what are the best parameters, they wanted some kind of feedback. So there was kind of an agreement to provide some limited set of analytics that was computed based on this information that was supposed to be only on the devices. And this solution implemented the PRIO system, the Bonnet Corrigan-Gibbs solution, which basically takes the input from the device, shares it into shares, sends it to two servers, together with a proof that this is, well, the kind of thing we use is just proving that you have a binary vector in the context of a bunch of buckets, which you're counting different things, like the number of exposure notifications sent around. And right, one big question for this type of solutions are who are your non-colluding parties? In that case, we needed two parties. We got three. That one of them was the Internet Security Research Group, which is also a certificate authority, so maybe you have heard them from this. One of them was NIH, and more specifically the Cancer Institute in NIH. And then there was another party which was called MITRE, which is a non-for-profit organization. The third one was just for the purposes of user interface for health authorities, which were not necessarily very savvy in using this data. But in that concrete application, which I think was driven by the fact that this was kind of for public good in some sense, there were a lot of parties kind of eager to participate and donate their work. So nobody was really paid for this work, and even kind of the cloud resources, because we wanted to be non-colluding all the way, so even different clouds were used by the different computing parties. They were also donated. This is not necessarily replicable in many of the other applications. So kind of just my conclusion of single versus two servers, I don't think one is necessarily better than the other. It really depends on your application. And this ISRG that worked with us at that point now has an aggregation helper service, which is called DVUp, which basically offers organizations that want to deploy such private analytics systems a kind of opportunity to hire them and be their like partner in this non-colluding assumption. When you're in a big organization, I think single server type of solutions are probably more likely to be your approach, just because you already have quite complex infrastructure. You're handling extreme volumes of data. So finding a partner or establishing, given the business relations, sometimes is challenging. But yeah, I think this was kind of my digression into when and how we were using these systems. And based on maybe our experience with this type of systems, we were thinking about like how should we improve our existing solutions, more in the context of this internal application that was the single server secure aggregation. So again, this is federated learning and analytics. When we talk about analytics, we are computing just histograms from the contributions of different clients. When we talk about federated learning, these vectors that we are aggregating are actually the gradients that the client have computed and are uploading to update your model. I think the one additional challenge for the second application is not really coming from the aggregation, but from the fact that you need to send the model down to the devices in order for them to compute these updates for the gradient. So sometimes this becomes the much bigger challenge because you're talking about big models being sent to the devices, and you need to figure out whether that works. And apart from being big models, there might be also sensitive models, so who knows?
How much is that actually used? You said this was like a service that's an option. Do you know if people are really interested in it?
So there are a couple of applications. They are all with relatively small models when we talk about federated learning, models that give you suggestions when you type for whatever emoticons. So yeah, I think they are relatively small because of this challenge. You have to send down the models, and there are many like communication, complexity, privacy issues, all kinds of things. So I think in terms of the real applications, we want to think much more about the analytics before thinking about the federated learning. But in this context that, yeah, in the federated learning, you are aggregating gradients, so whatever you develop as technique, that works for both. So a long line of works that I think kind of started because of this application at Google of secure aggregation, and this paper in 2017 was trying to derive a solution for this application. It's kind of leveraging the idea that what you will do is you will mask your inputs at each client with correlated keys. Like you will have some pairwise masks that all the clients share with each other, and then you will mask your input, you encrypt your input with these masks, and then you will send them up to the server. And when the server aggregates everything, these masks will cancel out, so the server can only find the output. So this nice, simple idea is kind of a good starting point, but then you face immediately the issue that these clients drop out all the time. So even with this simple idea, you had to establish this mask, so you are already more than one round. So you have to figure out how to handle these dropouts and make sure that you're not stuck at the server with something that you cannot get any useful information. So in order to resolve this protocols initial ended up having more and more rounds, introducing more masks. So there are two types of different masks. Ones are these self masks, the Bs. Ones are these hiding masks, the S's. And then you make sure that for each client, depending on whether the server claims it's dropped out or not, you will reveal only one of type of the masks. So for the bottom line guarantee that the server cannot try to present different dropout client subsets to different clients. And initially, this solution was requiring quadratic number of masks, like every pair of clients had a shared mask. Then there was a work that improved this to saying that, oh, it's so fine if you have only log n shared masks with your clients. One of the challenges that the people who were running this protocol were saying is that these inputs were quite long. So these masks were really PRGCs that were sent around. So the server and the clients were after that responsible to like run expansion and get the real length masks. And this was actually becoming bottleneck, like running these AESs expanding at the server to kind of in the reconstruction phase was a bottleneck. So then we had a solution that kind of said that you can do the aggregation before expansion when we shifted from these one-time pads into using LW encryption that offer this key and message homomorphic property that allowed you to first aggregate all the masks that are revealed for the purposes of the protocol and then do whatever encryption, decryption you might need in the protocol. So bottom line in this line of works, the eventual complexity that these protocols were having was first they were multi-round, like 5, 6, it depends on what you want to count. Then the client's communication and computation was down to the input length plus log of the number of clients. The server communication and computation was n times that of a single client. So this was this kind of line of works. I just want to mention, since I was already talking about some of these papers, that we also introduced how to do input validation, where input validations we defined as proving a norm bound for the input of the client, right? You have this vector that is the input of the client, and you want to bound L2 norm, L infinity norm. One interesting thing in that paper was that this statement that each client was proving was a little bit of a distributed statement because each of them was encrypting with keys that were correlated across the client. So the zero knowledge proofs had to prove that also this encryption is consistent across the inputs of the different clients. Adding this input validation resulted in making the complexity of the client to L times log n as opposed to the L plus log n. And the server scaled it the same way, scaled with the number of clients. So at some point, like there was this one line of work that was trying to do really like involve all the clients all the time for the reconstruction with the server. But there was also a different line of works where I think all but one of these papers are Antigonis papers, and then many other people in the audience that started introducing this notion that, oh, why don't we start using committees of clients to, in a sense, offload the work that all of the clients had to do in these initial protocols in order to enable the server to unmask and like reconstruct the output. Why don't we like delegate, in some sense, this work to a smaller number of clients in a committee that's sampled in an appropriate way? Some of them were thinking about these masks that I showed you were used for the masking of the inputs as sharing them and giving them across these committees. Some of them relied on semi-homomorphic PRGs and a lot of other neat ideas. I think what I want to highlight here, which was the thing that I thought needs to be improved, was that the communication and the computation complexity for the clients that were in this committee still depended on the total number of clients, and sometimes also the input length. And even though we're dealing with a small number of clients, it seemed like that in many cases this might be prohibitive for an actual implementation where, yeah, these clients are still your weak devices that need to participate in this complicated protocol. So I'm not going to give you all the details of the constructions here. I will have later a slide about the last work, OPA, which is a concurrent work with us, which kind of moves you to something very similar to what we also have in Willow. And also most of these protocols were still multi-round, except OPA. So now we come to this question of multiple rounds. And actually, this turns out to be quite important. And multi-round protocols usually work well when you have many fast and available clients. Right? If your clients are very fast, they can respond immediately to the requests, and are available all the time, that's great. You don't need to care about rounds. In reality, that's not the case. Clients run on very different operating systems. They're very slow in most cases, and they drop off for many reasons, right? You enter a tunnel, you enter the New York subway. We usually want to avoid sending data when the clients are not on Wi-Fi. We don't want to drain your mobile phone plan with sending probably many applications using this type of protocols. So as the systems people were saying is that like clients waiting on each other in any type of protocol is a real pain. And this messes up with your throughput. It's unreliable, introduces all kinds of complexity for the implementations. And they were really unhappy, like to the point that they were like, let's just get rid of this type of secure solutions. So in Willow was our kind of attempt to design a solution that gets rid of this important bottleneck, which was the multiple rounds. So we wanted to have a solution where clients that need to participate in this aggregation can just send their contribution in a single shot to the server. Also, one other thing that we were a little bit thinking about was coming from the fact that, as I mentioned, single server versus two server solutions, it's not necessarily clear which is better. And they will be useful in different applications. So ideally, you would like to have one solution that's easily instantiatable in one setting or in the other. So depending on what your application needs, you don't need to necessarily re-implement or have two different implementations that you choose one or the other, but you could easily like switch from one to the other as well. That said, a desirable feature is that like only the work of one server, the server that is the server in the single server instantiation, will depend on the number of clients and on the length of the inputs that clients are sending. We want to support this input validation. That's kind of expected by now. And one point here, which is probably not necessarily something that crypto people care about, is that you want to somehow facilitate extensions to other security protection mechanisms where these words here are masking references to trusted execution environments, because real system security people are not always happy with crypto solutions, and already TEEs are considered something that is an existing infrastructure. So you want to have something that you can say that you can easily kind of combine or augment by using this type of security mechanisms that they already offer and are not happy if you don't use them. In our solutions, we introduced some new names for the parties because we thought that this kind of architecture is conducive to having different instantiations for the different components, depending on what exactly security goals you try to meet, and also which of the system people you're trying to talk about. So what we have in our like overall proposals for the construction is that we want clients to be just encrypting their contributions, send them to a server who can do all the aggregation. And then we have these notions of a verifier and decryptor, where the verifier will be in charge of checking that the aggregation was done honestly, and then the decryptor will be in charge of decrypting the final output for the server. So these are different entities that we can define conceptually. And then in terms of how you instantiate them, well, you could definitely instantiate the decryptor and the verifier with this committee type of solutions, which is one option. And many of these constructions, they don't distinguish decryptor and verifier. This all happens at once. You can have a second server if you want to have a two-server solution instead of a single-server solution. And then should you be not so much in the crypto mindset, you can think of if you have some other trusted technology, can you plug it instead of the decryptor and the verifier? Where why would I be even like talking about this solution if I'm a cryptographer? Is that maybe you hope to minimize what computation you will put in this trusted, maybe vulnerable type of environments in order to like minimize the trust base that you want to require. So in that sense, we thought that this type of architecture is helpful for us, and it's helpful to design the protocol in this context. So desirable efficiency. I mean, the ideal efficiency, you really want this decryptor and verifier communication and computation to be independent of the number of clients and the input length. You really want only the server to work to depend and communication to depend on these two parameters. We didn't quite get to both of these goals. Okay, now I can just tell you some ideas of how our proposed solution works. So first, how do we get the efficiency of the decryptor that is independent of the number of clients and independent of the length of the inputs? Well, we apply this kind of hybrid encryption for the inputs, where we use two types of encryption schemes. One is key and message additively homomorphic encryption scheme, and the other one is additively homomorphic encryption scheme. So each client generates a random key for the key KHE and encrypts its input under this key. And then additionally, it encrypts the secret key that it generated for the encryption of its message under the public key of the decryptor. So now when you send this up to the server can add up the encryptions of the messages, which are the long encryptions, and then it can also add up the encryptions of the secret keys for the KHE, and the only thing it needs decrypted from the decryptor is the encryption of the short aggregate key. So now what you need to communicate to the decryptor is this encryption of the short key, and it's independent of the number of clients. Of course, right, this leaves the question, well, how are you sure what the server aggregated as is correct? This decryptor, we do propose to instantiate it with a committee of clients, and you can do this by using a threshold decryption scheme for this committee of the decryptor. Of course, yeah, you can think of other hybrid approaches to instantiate this decryptor committee. A little bit about why is this secure, because here the server eventually does receive the aggregate key that helps it decrypt the aggregate of the messages. So what you end up having is he has multiple encryptions that are under correlated keys. To prove the security of this, we use this hint RLWE hardness assumption that tells you that even if you give some additional information on the noise that is used in the underlying RLWE relation, that is also noise. Here, E and F are sampled from the noise distribution of RLWE, that this is still hard. there is a reduction from hint RLWE to RLWE. The previous reduction was losing quite significantly in the security parameter. There is some newer paper analyzing this that allows you to sample again the keys, the secret keys from small Gaussians, as opposed to having to sample from the uniform distribution before with the previous reductions. So you're almost not getting any security loss because of relying on this hardness assumption. So now a couple of words about the verifier. So what are we going to verify? Right, one option is to try to force somehow an aggregation on all of the inputs that the server ever received, which is, I guess, if I'm going for this ideal efficiency that says that my verifier will not depend on the number of clients, might be problematic. But then, like apart from this efficiency constraints, if we just think about the meaningfulness of this guarantee and the fact that you cannot prevent the server from dropping clients, you cannot prevent the server from impersonating clients, the meaningfulness of enforcing this aggregation across all inputs that the server received becomes less clear. And you, as I mentioned before, you need to rely on differential privacy for the protection of the aggregated output. So what we decided to do in terms of verification is that what we will be protect is the guarantees that you need for the differential privacy, which means that you can predict the sensitivity for your final aggregate. And what this means is that you want to guarantee that the server included each client's contribution at most once in this aggregate, that it didn't try to add it multiple times or somehow modify the input of the client in order to increase its absolute value, and this would kind of destroy your differential privacy guarantees that kind of crucially relied on you being able to compute the sensitivity. So this is the type of statement and guarantee that we'll be seeking from the verifier. And how we do this in practice is that our verifier would be checking that the server correctly aggregated all the encryptions of the secret keys for KHE. For some concrete efficiency, we actually move to a commitments, to homomorphic commitments of the secret keys that happen to be 32 bytes versus multiple kilobytes for the encryption. And what the verifiers do, which is still proportional to the number of inputs if it's a single verifier, is check that the aggregation was done correctly. And then in addition to this, we need to kind of include an additional zero-knowledge proof of knowledge at each client to prevent the server being able to manipulate these homomorphic encryptions that are coming from the client that are inherently very malleable. So we want to make sure that the only thing the server can submit in this aggregation is a valid input coming from the client and nothing derived from that input. If you want to reduce this dependence on the number of clients, so far the only solution we have is to say we have a distributed verifier or many verifiers. So you basically partition this aggregation tree, and each verifier is checking the sum on some subtree, and also but here the tree has sorted in sorted order all the input commitments. So what you're verifying is that for each chunk of the leaves, you have the correct sorted order. But maybe these things are more secure when you think about them as only attestation mechanisms versus mechanisms that enforce privacy. Also, because this has no reliance on any secret, you can think of things like certificate transparency that are already existing in practice, where people are verifying similar types of properties about commitments to keys. So you can use your imagination of how you can use this. I also wanted to say a couple of words about the concurrent work, which is Antigone and Harish's work, which is very similar to ours. If we think about the structure of this as clients encrypt their inputs, server aggregates, and then you have to somehow securely aggregate the keys to enable the server to open the correct aggregate messages. The difference is what in the third step, the OPA paper has two approaches that are based on homomorphic PRGs or key homomorphic PRFs. I feel like the underlying mechanisms that construct both our KHE as well as these primitives are very similar RLWE techniques. So what the difference, some of the difference of the complexities that the committee members' work still depends on the number of clients, but the positive side, some very nice features is that the decryptors or the committee members for the decryptors are single round and stateless. I think these two constructions probably will have will be preferable in the context of different applications. I think we were thinking that maybe the analytics maybe will be what we have in Willow, but if you go for federated learning, these approaches might have some advantage, better advantage. One thought I wanted to tell you about the adversarial model. Actually, the adversarial model that here makes sense is semi-honest server that is colluding with malicious clients. And why is this what makes sense in practice is that your server is a formal entity whose code is probably audited and could be checked. So deviating in the code that you're executing in the server is maybe easily detectable. But at the same time, you might have these rogue employees that could look at all the state of the server, and then they can kind of instantiate these malicious clients. So such a rogue employee effectively will have the view of a malicious client that can misbehave because you can claim anything, and this semi-honest server that is kind of colluding with the malicious clients. We just prove like security against malicious adversaries that control both clients and server, but this model does make sense here. I will tell you that we have some lower bound that says that if you have communication that's sublinear in the length of the input from the decryptor to the server, after the point where the server can choose to drop out clients, we seem to need the random oracle model. We don't know how to do a proof in the standard model. And I'm not going to show you how we construct this with the random oracle, but if you're interested, you can read it in the paper. This is kind of the costs that we have for our current construction. The decryptor is log n plus the size of the committee. And then the verifier, depending on how many verifiers you have, you can kind of split the verification across all the contributions of the clients. OK, and I'm 6 minutes over. I guess this is the advantage of being last. So yeah, this Willow this Willow system aims to kind of pick up the nice properties from the two server systems that allow you single shot contributions from the clients and suggests some kind of architectures which we think is useful if you're trying to implement this protocol. So thank you for your patience and your attention, and I'll be happy to answer any questions.
Any questions? So a quick question for the lower bound. You said it. So the impossibility is only if you don't allow random oracles.
Yeah, if we don't allow random oracle.
And there's a positive result?
Yeah, we'll show you how to construct a with random oracle, where essentially you get one small share from each input, and your share is you send the seed, the PRG seed for that share, and then you can later kind of in the simulation program that, the output of that. Yeah.
Cool. Thanks. So
sure.
Great. Yeah, thanks everyone for.
Very nice event.
Thanks all the.